Okay.
Okay, good talk to everyone. Davi Souza here. I'm the participant of mission 78 of Habitat Marte, and it's a pleasure. It's always a pleasure to be here talking with you. Today, I will be talking about the operation of a power station in a future Mars habitat. These are some topics that I will be covering during the presentation. Some of them will be talking about the design of a power station, also technologies. My background is in electrical engineering, so I will be focusing more on the side of the technologies and also the resources, the management of the habitat, the organizational structure. I will be talking also about the protocols, some protocols for the power station, and to finish my presentation, I will be covering up some guidelines and some topics associated to the spin-offs and sustainable development goals. To start my presentation, I really like to bring this picture because I believe it's the main base of each habitat that will be operating in space. So here it was taken from this paper called Minimum Number of Settlers for Survival on Another Planet. And as you can see, we have a pyramid. And in the base of this pyramid, we would have energetic systems and industrial systems. And they will be composing with the building, they will be composing the ecosystem, which will consider the atmosphere, ground, water, and living organisms. But as you can see, in the top of this pyramid, we would have the human factor. So no matter if we are considering energetic, industrial, and buildings at all, we always have to consider the human factors associated to the habitat, because we are still dealing with humans. The astronauts are humans, and they need to have the habitability of them are also important, the good habitability of them. Considering the internal design, this is the master plan proposed by Yashato during mission 47. And as you can see here, the power station is directly connected with the engineering facility. This has a logistical issue that I will be mentioning during the presentation. But as you can see, the power station is connected to the generation units, the main generation units. And as you can see, the solar farm composed with solar panels and photovoltaics. I'm considering here an eolic park in case of dust storms, just to have a backup generating system. And also a technology developed by NASA called nuclear power, 1 kilo nuclear power, or also QRST, which use nuclear fission to generate energy. And also in a small area for democracy to generate oxygen for the whole habitat, converting the CO2 of the Martian atmosphere into oxygen for the habitat. This is another picture just to present you the local location of the power station. And considering the internal design, it's considered that all facilities present a circumference shape with 8 meters of diameter and 3 floors. As I mentioned, the human factors are on the top of the pyramid, so it's necessary to provide the basic needs for the astronauts, an area for dormitory with beds, a small kitchen, dining room, a toilet, entertainment area. And it's also considered a food microproduction model because the situation of our mission is to imagine a possible threat of a virus in the habitat. So all of the members are isolated in each facility and they need to eat. And so that's why we have a food microproduction model, because each astronaut, each member of the mission doesn't have access for the main production area of the greenhouse. So also I'm considering here for more technical aspects, the electronic system monitoring area, a battery storage area, which I call the battery hub, And as I mentioned, the generation units, I'm considering some alternative generation units that will be inside the habitat, inside the facility. I'll be also talking more about this. And externally, I have mentioned it previously, the main generation units in the MOXIE. Just to have an idea, I divided these 3 floors. Like in the ground floor, we would have the social entertainment area, and also sleeping and toilet area. In the first floor, we would have some photobioreactors, which I'm considering as an alternative generation unit using algae, microalgae, which I will be talking more also. A monitoring area and an area for the protection systems. And in the second floor, we would have the battery hub. Some technologies to be applied. It's necessary to consider the electrical power subsystems will be responsible for generation, storing, and distributing the power to the whole systems of the habitat, such as life support systems, environmental control system for situ resource utilization, and other technological systems. We can consider some support technologies, just an example, the automated systems, but we'll be talking about other technologies for optimal operational procedures, data collection, detect failures of the systems, provide the balance of energy, and also take protective measurements. And some monitoring systems for power statistics, quality of energy, detection of faults over voltage, over current, short circuits, atmospheric discharges, which is very common during those storms, and energy fluctuations. And also some equipment, the batteries, the circuit breakers, fuses, transformers, protective relays, converters, and inverters to convert and to transform an AC to DC current, depending on the need for each equipment. And the equipment, all the equipment's status. For now, I will be talking about, I believe this is one of the most disruptive technologies also that has been using a lot in the power grid around the world. So the artificial intelligence has been used for energy forecasting and to provide reports. Just to have an idea, in the top top picture, you can see just an example how is the using of how is the forecast of a power. This is for eolic power generation unit. So there are some forecasts on the weather, the data from the measurement of the weather, and some historical data on the production of the system. It can be also considered for a photovoltaic system. So we would have some artificial neural networks that will be providing some insights and the forecast from 0 to 10 days ahead, but it can also be providing more days ahead depending on the capacity of the coding of the algorithm. Well, also from monitoring of the system parameters throughout the dashboard. As you can see here, in the other picture, a power plant monitoring with some index, some rates, some graphics on the dynamic of the system. And also I'm considering here this terminology HMI, which is human machine interface. So each kind that will be doing this interface between the technology, the machine, and the human being, it can consider like this, and need to consider also the human factors, the better visualization solutions, and also all of the possible outcomes that would be making the life of the astronauts easier, let's say like that, are welcome. This is also can be useful to accelerate maintenance team productivity and shorten repair time by prioritizing tasks. So a kind of the reports of, but also the reports of artificial intelligence can like just mention the specific area that needs some maintenance, some repair. So the maintenance team can go directly on the point that need to be fixed, and well, they will be losing more time looking for some problems. For the solar farm, I bring here some solutions. The build integrated idea. You can see in the right top picture, just an example. Also, the bottom right picture can be an example of good integrating technologies with solar panels. The malleable photovoltaic cells, also called OPV, it's organic photovoltaics. This is a new technology that can be also 3D printed. I'll be talking with more details. But you can see in the left picture, just an example of this malleable photovoltaics, and also heliothermic system. And I bring here this concept of photovoltaics called honeycomb. This is a technology called solar ore, and you can see here in the bottom right picture, these are small photovoltaic cells that have a kind of glass that will be directing a glass that will be directing all the sunlight, the radiation, the radiation of the sun that will go directly to the cell and will be generating more energy, of course. Other solutions for the solar farm, I'm considering the tracking system, as you can see in the right picture, just to have the optimal angle of receiving the radiation rays. And the captation by central tower, it can be considered as an heliothermic energy with using thermal energy, but also with solar radiation. As you can see in the left picture, we will have a central receptor that all the solar radiation or thermal radiation by the sun will be, if we consider a thermal energy generation, we will have a water pipe flowing through this receptor, and the sunlight will be heating this water, generating vapor pressure, and will be rotating a turbine to generate energy. And some issues associated to just dust storms, as I mentioned. This is a common case on Mars. As you can see also in these pictures, there is this fact that happened with the Mars rover Spirit, which the dust storm has cutted the energy of the rover and it doesn't work anymore. And so you can see the difference after a dust storm. And this is the data, the graphic of what happened. So here we have in yellow, we have the power generation of the rover with the solar panels. And once this measurement called tau, this is an index on the atmosphere of atmosphere opacity. So once the atmosphere get more particles of dust, the quantity of power generated reduces a lot, and so it cut the energy of the rover. Talking about rovers, the Perseverance, trying to overcome this issue, the Perseverance was sent, the recent rover arrived on Mars, was sent with technology using radioisotope power system, and using this technology here, the multi-emission radioisotope thermoelectric generator. This power system produces a dependable flow of electricity using the heat of plutonium radioactive decay as it fuels. It generates about 110 watts of electrical power at launch, and among the rover operates by ear, it's declining. And there are two batteries in case of peak demands, like if the rover has some more dense activities that will be consuming, demanding more power, the batteries will be giving some support on it. And the solutions to deal with the dust storm, I'm considering here two possible solutions. The first one would be the automatic photovoltaic cleaners. As you can see in the left picture, this is a kind of technology designed for deserts. It's work independently. It's robots, kind of robots, and has a water tank to wash the panels, but also works without water, using only a jet of air to reduce dust waste. So this is a case that would be interesting to Mars if you consider that water would be a resource that need to be saved a lot. So a jet of air can be a useful technology. And wind energy, this is considered because during the dust storm, the Vicky lander has collected this amount of wind speed from 17 to 30 meters per second. And for a turbine of 40 meters high, it can produce an amount of 120 to 300 kilowatts of energy. So this can be a possible solution, like when we have the dust storm and the solar panel are not generating well, this can be a system that will be like an alternative energy source for these specific moments. And the CRUSI technology, the kilopower, it was designed by NASA to be safe, long-lasting, reliable, scalable. This is the most interesting thing of these technologies. The energy need to be also energy efficient and compact to fit inside the rockets. So related to the scalability, in 2017, NASA tested and they have generated an amount of 100 watts of electricity with this technology, and they said that it can be scaled to 10 kilowatts and even megawatts of energy. So this can be like the main power source of energy on Mars. This is a technology that NASA has developed, and as you can see here, we have some radiators that will collect in the heat and will be heating the uranium core to generate this energy. For the battery hub, I'm considering the power storage area with all the batteries. Also, we'll need to have some batteries, heaters, and radiators, because if we are considering the fluctuations of outside temperature in the Martian habitat, and the batteries have chemical compounds inside of them, like their battery are made with chemical compounds association. So when we have some cold outside, when we have some temperature that are cold, it can be affecting the performance of these batteries. So that's why it's necessary the heaters and these radiators. Also a capacitor bank to avoid fluctuations. Also, there is a terminology that we call power factor, which determines the amount of energy that is really used as labor, and that other that like is just for reactive power. So that's why it's used these capacitor banks to avoid these power losses. And for also to overcome this issue, there are these other technology that are called FACT devices. For transmitter systems especially, and you can see here in this picture, in this flow diagram, when we have increasing power demand, just an example, when we have more machines operating at the same time, this can be considered as an unstable operation of the power system. So this FACT devices has an algorithm as an optimization tool And during these disturbed cases, this will be like providing a voltage stability and to minimize the costs due to energy loss. So just an example of how it operates. And as you can see in this left picture, the inverters and converters of AC and DC current. And also I consider this area of battery hub for battery recycling, because as I mentioned, there will be chemical compounds inside the batteries, and once they are not useful anymore, it's necessary to realize the astronauts will not be able to just, okay, let's put outside the habitat. So it's necessary to do a proper recycling of these batteries, see what can be reused and what can be discarded, and these need to be well discarded because the chemical compounds can also affect the health of the astronauts. And some other alternative generation units, I consider some technologies that can be used inside the habitat. So an electromagnetic floor, which has some like each step here can provide an amount of 5 watts of energy. This is used a kind of electroimaging to generate this energy. Also microalgae as a biofuel, mechanical energy of treadmills and bicycles. If you consider that astronauts will need to exercise an amount of 2 to 3 hours. So this can be useful also to generate some energy, like to feed the batteries in case of there is instability with the main generation units. And the wastewater to energy facilities, so just a kind of conversion of the sludge from wastewater to be turned into biogas, and also as substrate for plant production. And other technologies, the technology that I'm considering, this is very important, the telecommunication issue. This was recently added to my presentations because I noticed that this is a topic that isn't very much covered during the Habitat Marte presentations. And well, just to let you know, this is considered a kind of interplanetary communication system to provide a space communication channel. And just a possible, like a simple one, would be the mission control to the ground station, which have the antennas that will be directed to the habitat, will be communicating directly to the habitat, and then we'll be providing communication with the astronauts. So there are many other technologies, many things involved inside this channel, but this is just a simple one. And it's considered, this technology is for interplanetary service to provide a deep space network. As you can see in this picture, like many orbiters, many other, I'm not remembering the name, like the Voyager one that was sent outside the solar system. Well, we have this network among many technologies that communicate with Earth. Just to have an idea, this red one are made by laser, and the blue one are radio communication systems, radio communication systems. This would provide some detailed information about the solar system, solutions on radio astronomy, and applications for radio astronomy. Some features are to identify of these systems are necessary to identify a way to explore how deep space communication systems operates, and understand the possible communications threats from those communications channel already established with rovers, orbiters, orbiters on Moon, Mars, and other planetary bodies. And as I mentioned, the laser technology, this is just to have an idea of these technologies, the integration of technologies for space communications. So as we have the spin-offs, we also have the spin-ins. So these are the technologies that were developed for Earth that are also useful to space. So The laser communication has begun to be used here on Earth, so using laser sight, and with that, with increasing of technology and technological integration, they have come up with these technologies called free space optics. This is a viable solution to reduce losses associated with free space and have good reception, like signal stability, and the deep space optical communication, which use also this kind of technology for increased performance and efficiency and stabilizing the transport of data and information. And these are just two pictures, just to have an idea. The right one, you can see a communication established with a rover, just an example, a rover on Mars. So we would have an orbiter around Mars that would be communicating directly with the rover, and this orbiter will be a kind of restoring the signal and will be giving a light sight to Earth to establish the communication. Some possible resource to generate in situ or transport from Earth. As I mentioned previously, the photobioreactors for algae cultivation. It can be generated in the habitat for edible biomass, biofuel, CO2 to O2 conversion. So this can be also an alternative to MOXIE, operates together, and also effluent treatment. And as you can see in the right picture, these are some applications proposed by NASA with the integration of green and space technologies. So these are some algae applications. And also I have founded this other technology, algae-powered fuel cells. This is a biophotovoltaic cell which can provide an amount of 0.5 watts per square meter of area. Well, and other, as I mentioned, the MOXIE would be responsible for the production of oxygen, and also, as I mentioned, can be also operating together with other technologies, just as such as the algae cultivation, to reduce consumption costs. And the MOXIE technology was a technology, a prototype developed to be sent aboard the Perseverance rover. It was already tested recently. They have produced the first molecule of oxygen on the Martian atmosphere. And just to have an idea, the systems operate as producing the molecular oxygen from the atmospheric carbon dioxide from the Martian surface, just to have an idea, which is composed by 96% of CO2. Related to the management, I'm proposing this for the grid. We will have the power station. We will have the integration, 2 units of alternative energy. So of generation units, the alternative generation units, and the main generation units that will be monitored and also protected, both of them. And so we would have the connections with the social areas, the food microproduction, and the sleeping area. This is only for the power station, but it's the same approach for the other stations. And for the battery hub, we will have the power control and the recycling area. And just in case of, that's why I have put the battery hub in the 2nd floor, because in case of any problem, specific problem, even fire inside of the habitat, it can be started in emergency decoupling. So depending on how complicated is the situation, how vital is the situation, like it can be the decouplement of like the wires, only the wires, but also it can be decoupled the whole like the whole floor, so the rest of the station will be safe and will be like avoiding the fire spreading and other possible issues, hazards. This will be the whole habitat will be connected infrastructures, and also I'm considering here this connection with the engineering center. The logistic idea of the engineering center would be also to have redundancy systems, especially on protection systems. So we would have the first protection system areas inside the power station, and in the engineering center, we will also have the other protection systems in case of any protection system, like if we have one protection system that doesn't work well, that didn't have activated in case of emergency, we would have the engineering center, also the engineering center protection system operating well. And the professionals will be capable to conduct experiments, aim at a great structure and system maintenance, and also the idea of collaboration. So once the virus is not anymore in the habitat, it's important to have this collaboration between the power station astronauts, the astronauts from the power station and the astronauts from the engineering center, to have developed new technologies and propose new solutions for the grid, maybe optimize something, develop new algorithms. So also the idea of continuous improvement engineering. And the waste management for the structure, it's necessary to analyze what will be or what was discarded, see if there is any possibility to recover this equipment. If not, it's necessary to provide a reuse. If so, it's necessary to provide a reuse logistic. If not, a disposal logistic. Some permanent positions here that I'm considering for the power station will be the power manager, the astronaut responsible for conducting good practice, awareness, and development of monitoring and maintenance schedules, and the chief engineer would be the professional qualified to conduct in situ activities on the power systems, will be also responsible for installation of equipments and maintenance routines. And some functions, so I'm considering 2 positions, but it can be like switched on functions. It's not necessary to have like the chief engineering as the leader of the structure. So it will be, I consider that this will be depending on the necessity of the system. So if we are in the beginning phase of the habitat structuration, so we are installing the system, the main systems, it will be more useful to have the chief engineer as a leader to have more this view of developing the systems, putting into operation. And once we have only the operational aspect, the operational side of the system, the electrical systems, maybe the power manager would be more useful to be the leader. So just to have an idea. Some other functions are the sub-chief, system analyst and IT professional, maintenance officer, and some duties for the chief, specifically for the chief, for the leader, will be delegate functions, give instructions, establish schedules, promote the rotation between the respective center and other infrastructure of the habitat. So just to have this kind of collaboration and sharing of knowledge between the other facilities, like just an example for the greenhouse, if there is need of any maintenance on an electrical system, the lighting system. So the chief would be delegating like, okay, it's necessary to conduct the maintenance, the repairment of the lighting system of the greenhouse, and to have this rotation of tasks, and also with other astronauts. So it's necessary to have an engineer from the engineering center on the power station for a while to conduct any kind of activity. So it will be depending on the case. For the astronaut training program, I am incorporating some basic features. just some ideas that are really necessary for all astronauts. The first one would be sustainable human presence in space. They need to have this idea. Also to support long-term effects of isolation, practice to reduce costs and technical risks in overall vital systems. So life support, especially life support systems, environmental control. These are, I believe, these are the main important ones. Have some courses, some training focused on basic understanding of the handling and maintenance of electrical systems. So I consider that is really important. All of the astronauts have the basic understanding on everything, no matter if it is agriculture, electrical system, because if happens something, in this case of isolation, if happens something on an electrical system of the health center, so it's necessary also for the astronaut responsible to have an astronaut responsible to have a, like, okay, I believe it's necessary to do something or some other thing, and have this contact with the power station chief, like to just giving some guidelines and monitor the activities. Have this capability of analysis of risks and failures, allowing the generation of monitoring reports of the systems, meetings for crew decision making, not only inside the structure, but with the whole habitat, and new skill to overcome emergencies based on situations identified at Mars, having some simulations. I always consider that because from what we know for now about Mars, it's only based on research that we have conducted here on Earth, the analog trainings, and other situations inside the ISS. So maybe on Mars, it can happen in a different way. So there can have, the astronauts can be dealing with some situations that are not expected, and they will be knowing that when they really arrive on Mars. That's why it's important to have this idea of resiliency. Some videos for astronaut training. I bring here just main ideas about some technologies that I presented, the solar ore, and that photovoltaic cell of honeycomb, also about the kilopower nuclear system, the MOXIE, and the Copia robot. This is the robot that I have mentioned for cleaning the photovoltaic cells. And also this really useful video made by National Geographic, just talking about generating power on Mars. They are considering the solar farmers for main generation system. But as you can see, there are different solutions, like this one using it's called, I'm not remember exactly the word in English, but this kind of panel that will be focusing all the rays of sunlight into this focus. So we would have we'll be concentrating the heating, maybe the heating or maybe the electrical power here to generate the energy, and also some deployable solar panels. This is just, I have printed the video here, and well, as you can see, we will have solar panels that are not deployed and after deployment. And some resource for 1 week. I'm considering the energetic needs, the dimensions of all the systems, the energy supply, water supply, heating, and air conditioning system will be determined by the number of inhabitants and the amount of vegetation. So this can be differently based on the mission goals. And according to this associate administrator of NASA, James Reuter, he's considering an amount of 40 kilowatts of power demand on the surface of Mars. So if we have the crusty technology operating well and well scalable, it can be a good solution, like to provide this demand. But as I mentioned, it's not that useful to have only one technology. It's necessary to have the idea of redundancy and alternative units of energy in case of failures or other problems that may happen. Considering the basic needs for astronauts, for 2 astronauts inside the structure, the diet, as the systems, the diet will be different for each individual, for each astronaut, will be determined by weight, height, the biotype, the routine of the astronaut, so it can be different, but I am doing here an assumption of 2.1 kilograms by astronauts for a daily consumption. Just to let you know, this is not a number that I bring here from my mind. These values were taken based on results from this article, Greenhouse Production Analysis of Early Emission Scenarios for Moon and Mars Habitats. This was a research conducted in Eden ISS, inside of FAG greenhouse, so in Antarctica. And they have come up with some approaches for harvesting events, and they have realized that this amount of daily consumption can meet astronaut daily demand of biomass, but also meet the biomass storage status. So if the astronauts consumes this amount of food per day, the storage status increases by time. And for a week, doing the calculations here for 2 astronauts, will be an amount of 40 kilograms. And for food and on potable water, I'm considering here 3 liters of water by person, and a week consumption of 42 liters of water. And this is a really interesting thing because this is also a number based on what we already know on human health here on Earth. So in Mars, it can be different. It can be like having some different values, maybe more, maybe less. Some guidelines will be provided to other facilities, some indicators of consumption and control use of energy, in control of energy use, economic practice to be added to the astronauts' routines, basic guidelines and training for handling and preventive maintenance of electronic equipment. So in any case of failure of there is a system that, okay, a system just stopped to operate, and what now? What can be done? So basic, as I mentioned, the basic understanding on what can be done on the electrical system, it's important. Smart reports capable of establishing the correlation between the different variables of the system, current, voltage, power consumption, power generation, and just with the goal of maximizing the energy efficiency. Protocols for energetic guidelines, just on how to use the energy, and warning about failures and emergencies. On protocol side, for the system, for the facility, I bring here this specific, this idea to track system notifications related to deviations and irregularities. So this is really important, especially for the vital systems. It's important to have this remote monitoring because of failures, if happen anything, the astronaut need to know and need to do something as soon as possible. So I'm consider here a controller for the systems, and this controller will be a kind of interface between the grid, the generators, and the batteries, and the infrastructures, the high loads, that systems, that specific technologies that has a huge consumption of energy, and also the protection systems. So this controller will be also responsible, like, okay, we have, just an example, we have a protection system that didn't operated by himself. So we can have like a kind of redundancy on this controller, and also to have this interface with the status of equipment and say, okay, and say to the machine operator, okay, there are specific protection equipment that didn't work. Like happened a short circuit and that equipment didn't work. So this is also important to be monitored. Some protocols of safety. I consider the fast isolation procedures. Case of failures, faults, short circuits, lightning strikes, as I mentioned, common sandstorms. Start the emergency decoupling, as I mentioned, can be just the wires. Okay, let's decouple the system and separate like the main generation units from the habitats, from the batteries, and have everything decoupled. But in case of bigger failures, bigger emergency situations, start up another procedure more more intense, let's say like that. And the protection equipment and sectioning of generation plants and sectioning of the generation plants and the habitat will be activated to avoid widespread losses. And the people inside of the structure must start the process of checking the status of protective equipment. So it's not only like, okay, the protection system are, the maintenance of the systems, what was done of this equipment was done last week. So it will be operating well. No, it's necessary to check if to make a double check if this equipment really operated, because as I mentioned, it's necessary to avoid widespread losses. And if necessary, establish an order to deactivate the main system, the main generation units, and activate only the bank of generators, the alternative generation units, and the backup batteries. And other protocols can be system recovery, like if a solar panel stopped to operate, happens something that's not operating anymore, or even like the kilopower just exploded, and it's necessary to conduct an AVA to monitor what happened and see and assess the affected side, and perform the inventory of losses and see if it's possible to recover something and provide the recovery schedule if possible. And have some guidance to the whole station, will be inform the mission members about the maintenance and repair of energy resources. Occupancy and entertainment will be the alternation of monitoring routines, socialization practice proposed by the health center, areas for relaxation, exercise, games, and also I consider the operational activities involving the cultivation of food and interaction with plants, its capabilities to promote a good, a positive impact on humans' psychology. Protocols for food microproduction. This is an idea that I bring from the presentation of the greenhouse. This was presented on the paper Agriculture in Mars, Habitat Marte findings, presented by me and Professor Julio last year during the IAC. And we came up with these routines and these developed activities from the operation of biohabitat greenhouse on Habitat Marte here in Brazil. We came up with some routines on management, maintenance, recycling practices for the greenhouse, and also some harvesting and processing routines. And some activities to be developed would be the analysis, diagnosis, ensure the circularity, assure the fidelity of methodologies, the standardization of this process, some orientations, and detect possible failures. The main idea of these guidelines would be to ensure these features here: the food logistics, the risk management and prevention, monitoring reports, and waste management. So some reports that would be sent to the greenhouse, and some data, and also to have this food logistics, like, okay, we have that amount of food produced in the power station, so we will deliver only that specific amount from the greenhouse. Protocols for 3D printing consider cooperative work, as I mentioned previously, between the energy center and the engineering center, the power station at all, for the production of eco-device, organic electronic devices, equipment coverage shutters, as you can see in the right picture, like this. This was for a circuit, a simple electronic circuit, but we have here the shutter, the coverage equipment for the systems. And also, this is really interesting, also the conductors and filaments produced by 3D printers. This is a really simple circuit, just to turn on LED. So you can see here how it is effective. Another solution for 3D printing, as I mentioned, the use of algae. Why not a 3D printed algae? This is a really recent technology that was developed. I found this is really interesting because, well, this microalgae is printed on bacterial cellulose. It's a novel bioprinting technique into these living resilient materials that is capable to conduct the photosynthesis. And this is considered a sustainable living material during its biodegradable and recyclable nature. And this is a new oxygen producing material also. So it's kind of possible to 3D print oxygen, let's say like that. Not directly, but there is this possibility. And the OPV, the organic photovoltaic cells, some features is the low cost manufacturing, which reduces the cost by 50%. There are many abundant materials in nature to print these photovoltaics, these solar cells. The flexibility, the malleable photovoltaics, low weight. This is important if we consider the payload for mission, future missions to Mars. A proper disposal, so these are organic materials, so it can be more easier disposed if we consider like the regular photovoltaic cells. And the possibility to be 3D printed. And just to have an idea on numbers, these solar panels are 20% more efficient than traditional ones. So this can be also a solution to increase the performance of the power systems on Mars and also Earth. Talking about Earth, the spin-offs, the technologies developed to space that can be useful here on Earth, some technologies and outputs that could be applied here on Earth can be the idea of self-sustainable electricity, the renewable energy that is really common now. The use of structures, the construction of structures with efficient resource saving, also called the eco-friendly structures. Just to have an idea here, this is a roof that has solar panels, but also allow the sunlight go inside of the building, so it saves energy at the same time that produces energy. The livers with lowest possible handling and better performance for the smart grids, the idea of smart grids that is really common for now, using AI and other technologies, and the development of other environmentally friendly technologies with carbon footprint reduction. Just an example of the OPV, which, as you can see here, each square meter of the OPV avoids the emission of 120 kilograms of CO2 per year. So this is a big amount. Imagine a positive impact that it can generate. Some guidelines to be applied on daily life on Earth. As I mentioned, the idea of sustainable energy production, creative ways to deal with solar energy issues, development of new technologies and systems to improve safety and reliability of energetic systems, easy assembly and maintenance with optimal procedures, solutions to keep the confidence related to control of power and its protection systems, reuse of materials and recycling practice, energy consumption management, investment in research on different ways of adding positively to the global energy metrics. And to conclude my presentation, I bring here the impact to sustainable development goals. This is really important. I always beat in this topic because this is really important. We need to have this idea in mind, especially us that are from the space sector, because space has the potential to help us on Earth. Space have the potential to benefit all of us, our ecosystem, well, in many ways. So the sustainable development goals shows that all of this that I have presented today can be considered in these topics, especially the technologies, on the technological aspects. So the affordable and clean energy industry, innovation, infrastructure, responsible consumption, decent work and economic growth. And the main one is the climate action. So if are not us that show people that space technologies are useful to us on Earth, who will do that? We have the knowledge. We know that space technologies can be useful. And if we not say to people, hey, there is the possibility to apply this technology from space here on Earth, this will be avoiding some impacts on climate change. So let's use it. Why not? Let's try to be agents of transformation on our communities, our countries, and in the global perspective really shows the space is here to help and to improve people's quality of life. So these are my reference. Thank you very much. For those who will be watching this presentation later on YouTube channel of Marte, this is my email. Feel free to contact the live questions, and now I'm open to questions of the crew. Thank you.